For thousands of years, people have looked at the sky and wondered what those things were moving around their heads. One of the ancient mathematicians who made quite efforts understanding the universe was Ptolemy. He introduced his opinion from 180 to 170 AD and believed that Earth was at the center of the universe in a way that Sun and other planets revolved around it. Well, this idea was assumed to be right for about 1500 years until Nikolai Copernicus came with the idea of heliocentric universe, in which the Sun lies at the central point. Meanwhile, Galileo Galilei provided his own evidence confirming Copernicus' model. On the other hand, a Danish astronomer named Tycho Brahe was taking a very precise measurements showing that Moon orbits the Earth, but mistakenly concluded that the Sun goes around the Earth. After Tycho Brahe's death, Johannes Kepler had full access to Brahe's papers and founded his own laws of planetary motion. Kepler made accurate mathematical measurements and realized that despite the fact that Earth goes around the Sun, it does not orbit in a perfect circular way. In fact, planets, including Earth, move along an elliptical path with having the Sun as one of the two foci. This statement is referred as the first law of Kepler. The reason behind this phenomenon is basically due to the fact that planetary movement is a type of non-circular motion in which the magnitudes of velocity, radius, and mass are constantly varying. In other words, each planet is under gravitational effects of other celestial bodies, which distorts space-time curvatures. Anyway, in our solar system, eccentricities of planets' paths are so small that their appearance is very close to a perfect circle. Kepler continued analyzing and realized that the speed of planets changes depending on their location in the ellipse. He declared that the farther a planet from the Sun is, the less its velocity gets, geometrically meaning that the radius vector connecting any planet to the Sun sweeps out equal areas in equal time intervals. Kepler was attempting to establish a mathematical pattern in the periods of planets, and eventually, 10 years after publishing his first and second laws, he came to an interesting result. He discovered that the square of the orbital period of a planet is directly proportional to the cube of its average distance from the Sun. Thus, for any revolving planets, we can write this equation. T2 divided by T1 squared equals to R2 divided by R1 cubed, which equals to a constant magnitude. But in fact, Kepler had no idea while all planets obeyed the same law. Some years after his death, the famous English physicist Isaac Newton explained the truth behind this natural arrangement. According to Newton's universal law, the gravitational force between any planet and the Sun equals to their multiplication of masses times g divided by squared r. Newton proved that any orbital motion is caused by a centripetal force, and in the case of planetary motion, gravity plays this role. In fact, this force equals to square root of the velocity times mass divided by the radius. However, be careful that in an elliptical path, the force vector is not necessarily perpendicular to the velocity vector. By simplifying the following equation, we obtain the planet's velocity in terms of gravitation, in which velocity equals to root of g times m divided by r. Moreover, for a particle traveling on a circular path, it takes 2 times p times r divided by velocity to complete one revolution. The required speed derived from this relation equals to 2 times p times r divided by capital T. Now, if we rewrite our assumptions and square both sides, we will come to an equality, where cross multiplication leads us to this. T squared equals to 4 times p squared times r cubed divided by g times ms, in which T1 and T2 belong to two different planets. Dividing these two relations by each other gives us the Kepler's third law. This is how Newton succeeded to demonstrate his theory. Hope you have enjoyed watching this video, and feel free to ask us any of your questions.